Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on gases. Let's go ahead and get started. Problem number 1 says, which of the following sets of conditions would be least likely to result in ideal gas behavior? A says high pressure and low temperature, B says low temperature and large volume, C says high pressure and large volume, and D says low pressure and high temperature. Now, in general, the ideal gas law is a good approximation of the behavior of real gases, and ideal gas behavior is described by the ideal gas law, PV equals nRT, just like we saw in lecture. Now, this equation assumes that the gas particles do not interact with each other and they occupy no volume themselves. And these assumptions are generally valid under conditions of low pressure and high temperature. However, at high pressure or at low temperature, real gases deviate from ideal gas behavior. Let's conceptually work through deviations due to pressure and deviations due to temperature so that we better understand the statements we just made. The first statement was that real gases deviate from ideal gas behavior at high pressure. Why is this true? Well, as the pressure of a gas increases, the particles are pushed closer and closer together. At high pressures, the volume of these particles becomes significant compared to the total volume of the gas. And this is because under high pressures, the gas particles are squeezed much closer together, which means that the space they occupy cannot be ignored. And this causes the actual volume of the gas to be less than that predicted by the ideal gas law. The second point we made was that real gases deviate from ideal gas behavior at low temperature. Why is this true? Well, at lower temperatures, gas particles move slower since they have less kinetic energy. This slower movement allows the attractive forces between molecules to have a more pronounced effect. So in other words, the particles, they spend more time in close proximity to each other, allowing for intermolecular attractions to pull them together. Now, this deviation due to intermolecular forces is just not accounted for in the ideal gas law. So with all that being said, the correct answer to problem 1 is going to be A. At high pressure and low temperature, real gases deviate from ideal gas behavior. Let's move on to problem 2. Problem 2 says, what is the density of neon gas in grams per liter at STP? Now, STP stands for standard temperature and pressure, which is defined as a temperature of 273 Kelvin and a pressure of 1 atmosphere. In addition, at standard temperature and pressure, 1 mole of an ideal gas occupies 22.4 liters. Keeping that in mind now, density is defined as mass over volume. For our system here, the mass of 1 mole of neon gas equals 20.2 grams. And then at standard temperature and pressure, 1 mole of neon gas occupies 22.4 liters. So density is equal to 20.2 grams divided by 22.4 liters. Now we can approximate these values to 20 over 22, and this simplifies to 10 over 11, which is approximately equal to 0.9. Looking at our answer choices here, the value that's closest to that is going to be D. And so the density of neon gas at standard temperature and pressure is 0.9018 grams per liter. Next up, we have problem 3. Problem 3 says a leak of helium gas through a small hole occurs at a rate of 3.22 times 10 to the minus 5 moles per second. How will the leakage rates of neon and oxygen gases compare to helium at the same temperature and at the same pressure? A says neon will leak faster than helium. Oxygen will leak faster than helium. B says neon will leak faster than helium. Oxygen will leak slower than helium. C says neon will leak slower than helium and oxygen will leak faster than helium. And then D says neon will leak slower than helium and oxygen will leak slower than helium. Now, the rate at which a gas leaks through a small hole can be described by Graham's law of effusion. And Graham's law states that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. Mathematically, this can be expressed as the following equation. Here, R1 and R2 are the effusion rates of the two gases, and M1 and M2 are their respective molar masses. Now, if we want to answer this problem quickly, we just have to keep in mind that based off of Graham's law, a gas with a higher molar mass is going to leak more slowly than a gas with a lower molar mass. Therefore, both neon and oxygen gases are going to leak at slower rates than helium because they both have more mass than helium. Therefore, the correct answer to problem 3 is going to be D. Neon will leak slower than helium and oxygen will leak slower than helium. On to problem 4 now. Problem 4 says a 0.1 gram piece of magnesium is placed in a beaker of hydrochloric acid. Hydrogen gas is generated according to the following equation. We have magnesium reacting with hydrochloric acid to give us magnesium chloride and hydrogen gas. Now the gas is collected over water at 25 degrees Celsius and the pressure during the experiment reads 784 millimeters of mercury. Now, the gas displaces a volume of 100 milliliter, and the vapor pressure of water at 25 degrees Celsius is approximately 24 millimeters of mercury. Based on this data, how many moles of hydrogen are produced in this reaction? And here we have our ideal gas constant. Now, understanding the principles of gas collection over water and the ideal gas law are going to be really important to correctly determine the amount of hydrogen gas produced. We're going to first need to account for the vapor pressure of water to accurately measure the hydrogen gas pressure, and then we can use that and the ideal gas law to calculate the moles of hydrogen. Let's get started with that first step. When a gas is collected over water, the total pressure measured is going to be the sum of the pressure of that gas and the vapor pressure of the water. And this is because the gas collected is saturated with water vapor. Now, to find the pressure of the hydrogen gas alone, we're going to need to subtract the vapor pressure of the water from the total pressure. Now, the total pressure is 784 millimeters of mercury, and then the vapor pressure of water is 24 millimeters of mercury. And when we take the difference between these values, we get 760 millimeters of mercury. This is exactly equal to 1 atmosphere. And the reason why we want to write it as 1 atmosphere is because in the next step, we're going to use our ideal gas law, and we want our pressure to be in units of atmosphere, so everything cancels out appropriately, and we get our final answer in units of moles. Now that we have the pressure, let's go ahead and write down our ideal gas law, PV equals nRT. And we're going to be solving for moles of hydrogen gas. So let's go ahead and isolate that variable n and move all the other variables to the other side. So what we're going to get is n is equal to PV over RT. Now, our ideal gas constant is the following value, 0.0821 liters times atmosphere over moles times Kelvin. Now, we want all our variables to have appropriate units so everything cancels out except moles, and that means our final answer will have units of moles, which is exactly what we want to accomplish. Now, we already have pressure in atmosphere, so this is good. We have the volume, but it's not in liters. We're given the volume to be 100 milliliters. We can easily convert this to liters by dividing this value by 1,000. That gives us 0.1 liters. So now our volume's also good. The last thing we need to check is our temperature. We need our temperature in units of Kelvin, but unfortunately we were given our temperature in degrees Celsius, so we're going to have to convert it. We're going to convert it to Kelvin by adding 273. This gives us 298 Kelvin. Now we have all the variables we need in all of the appropriate units. We can just go ahead and plug in the values. Pressure is 1 atmosphere. Volume is 0.1 liters. This is going to be divided by our gas constant, 0.0821 liters times atmosphere over moles times Kelvin. And then our temperature is 298 Kelvin. Now our numerator is really easy to calculate. 1 times 0.1, that's going to give us 0.1. And then for the denominator, we can approximate this value to 0.08, and we can approximate this value to 300. And we can multiply these together. Now here's a really easy way to do this. We can multiply 8 times 3, that's 24, and then we can add in those 2 zeros. That's not our final answer because this would be the answer if we were multiplying 8 times 300, but we are actually multiplying 0.08 times 300. So to get the correct answer, we need to move the decimal place 2 places to the left to get our correct answer, which is going to be 24. Now I also want to show you what units cancel out and what units do not. Atmosphere cancels out, liters cancel out, Kelvin cancels out, mole is the only unit that's left, so our final answer is going to have units of moles. Now, how do we do this calculation? 0.1 over 24. What I'm going to do is I'm going to multiply the numerator and the denominator by 10. This gives me 1 over 240. And then I'm going to go ahead and approximate that to 1 over 250. This is going to be a much easier calculation, and let me show you why. We know that 1 over 25 is equal to 0.04. Then that means 1 over 250 is going to be very similar, but with an extra 0. It's going to be 0.004. And this is equal to 4 times 10 to the minus 3 moles of hydrogen gas. All right, so let's look at our answer choices, see which one best aligns with that value. That is going to be answer choice B. So 4 is B. Wonderful. Let's go ahead and move into problem 5. Problem 5 says ideal gases, blank, statement 1, have no volume, statement 2, have particles with no attractive forces between them, and statement 3, have no mass. Let's go through these one by one. Statement 1 says that ideal gases have no volume. Now, the ideal gas assumption is that particles have negligible volume and can be considered point particles. Now, there's an important distinction to make here. While each particle within the gas is considered to have negligible volume, ideal gases as a whole certainly do have a measurable volume. Just think about your ideal gas law. PV equals nRT. V is volume. Ideal gases have volume. This makes statement 1 incorrect. Statement 2 says have particles with no attractive forces between them. This is correct. Ideal gas theory assumes that there are no intermolecular forces between gas particles. So this means that the particles move independently of each other and they do not interact except for elastic collisions. So statement 2 is true. Statement 3 says that ideal gases have no mass. This statement is incorrect. Even in the ideal gas model, gas particles have mass. The assumption is that they have mass but negligible volume and no intermolecular forces. So statement 3 is also incorrect. The only correct statement is statement 2, which makes the correct answer for 5, answer choice B. Let's do problem 6. Problem 6 says which of the following best explains the difference in ideal behavior between nitrogen and fluoromethane gas. Now, nitrogen gas is N2. Fluoromethane gas is CH3F. CH3F. Okay, let's read through these answer choices first. A says nitrogen gas is more ideal because it is smaller and forms stronger intermolecular interactions. B says nitrogen gas is more ideal because it is smaller and forms weaker intermolecular interactions. C says fluoromethane is more ideal because it is larger and forms stronger intermolecular interactions, and D says fluoromethane is more ideal because it is smaller and forms weaker intermolecular interactions. Now, two main things to keep in mind that's going to help us answer this problem is the size of the gas molecules and intermolecular forces. Smaller molecules tend to behave more ideally because their volume is negligible compared to the volume of the container. In addition, weaker intermolecular forces result in more ideal behavior because the gas particles interact less with each other, behaving more independently. So looking at these two gases, nitrogen gas and fluoromethane gas, nitrogen here is a diatomic molecule with relatively small size, and fluoromethane is a larger molecule than nitrogen. Now, looking at nitrogen, nitrogen is going to form weak intermolecular forces, primarily van der Waals forces due to the nonpolar nature of nitrogen gas. Fluoromethane gas, on the other hand, it's going to form stronger intermolecular forces, including things like dipole-dipole interactions due to the polarity that's introduced by that fluorine atom. So keeping that in mind, the correct answer is going to be B. Nitrogen gas is more ideal because it's smaller and because it forms weaker intermolecular interactions. Beautiful. Problem 7 says the kinetic molecular theory states that blank. Let's go ahead and remind ourselves about the postulates for the kinetic molecular theory, and then we're going to read each answer choice one by one and work through it. All right, so as a reminder, the kinetic molecular theory of gases is a model that explains the behavior of gases at the molecular level, and it makes several key assumptions about the nature of gas particles and their interactions, and this helps us derive the ideal gas law and obviously explain the properties of gases. First point we want to go over and remind ourselves of is that gas particles are in constant random motion. This explains why gases fill their containers and then exert pressure on the walls. Second point, the volume of gas particles is negligible compared to the volume of the container. This means that most of the volume of a gas is empty space. Third point is that gas particles do not exert attractive or repulsive forces on each other. They interact only through elastic collisions, and that leads us into point 4. Collisions between gas particles and with the walls of the container are perfectly elastic. This means that no kinetic energy is lost in collisions, it's only transferred. Last and final point is that the average kinetic energy of gas particles is directly proportional to the temperature in Kelvin. So this implies that as temperature increases, the kinetic energy of the gas particles also increases. Keeping those key assumptions in mind, let's work through each of the answer choices. A says the average kinetic energy of a molecule of gas is directly proportional to the temperature of the gas in Kelvin. This is true. So according to the kinetic molecular theory, the kinetic energy of gas particles increases with temperature. So this statement is true. It's actually the correct answer, but we're still going to work through B, C, and D. B says collisions between gas molecules are inelastic. This is false. Kinetic molecular theory states that the collisions between gas molecules are elastic, meaning that no kinetic energy is lost in the collisions. So this is incorrect. Answer choice C says gas particles occupy discrete areas of space. Now, this is false. Kinetic molecular theory assumes that the volume of individual gas particles is negligible compared to the volume of the container. They do not occupy discrete areas, but rather are considered point particles. So this is also incorrect. Last answer choice says that all gas molecules have the same kinetic energy at the same temperature. Now, this is false. While the average kinetic energy is directly proportional to temperature, individual gas molecules do have a range of kinetic energies due to their constant random motion and their collisions. So all in all, the correct answer here for problem 7 is going to be A. Let's move on to problem 8. Problem 8 says the plots of two gases at standard temperature and pressure are shown below. One of the gases is 1 liter of helium, and the other is 1 liter of bromine. Which plot corresponds to each gas and why? A says that curve A is helium and curve B is bromine because helium has a smaller molar mass than bromine. B says curve A is helium and curve B is bromine because the average kinetic energy of bromine is greater than the average kinetic energy of helium. C says curve A is bromine and curve B is helium because helium has a smaller molar mass than bromine. And D finally says curve A is bromine and curve B is helium because the average kinetic energy of bromine is greater than the average kinetic energy of helium. Now, to determine which plot corresponds to which gas, we need to understand the Maxwell-Boltzmann distribution of molecular speeds. This distribution shows the range of speeds of molecules in a gas at a given temperature. There are several important points to consider here. Point 1. The average kinetic energy of gas molecules is directly proportional to the temperature. And since the temperature is the same for both gases, their average kinetic energy is the same. This allows us to eliminate answer choices B and D. Now, the second point is that for gases with the same average kinetic energy, the lighter gas will move faster than the heavier gas. So in other words, helium will move faster than bromine. Therefore, helium gas corresponds to curve B, which has a higher average speed, and bromine corresponds to curve A because it has a slower average speed. This makes the correct answer for problem 8, answer choice C. Beautiful, let's move on to problem 9. Problem 9 says at sea level and 25 degrees Celsius, the solubility of oxygen gas in water is 1.25 times 10 to the minus 3. In Denver, a city in the US that lies high above sea level, the atmospheric pressure is 0.8 atmosphere. What is the solubility of oxygen in water in Denver? Now here, understanding Henry's law can help us determine how changes in pressure affect the solubility of a gas. The solubility of gases in liquids is directly proportional to the atmospheric pressure as shown by Henry's law. So we can set up a similar expression to this so that we can solve for the solubility of oxygen in Denver. So what we can write is that the solubility of oxygen gas at sea level is divided by the pressure at sea level, and this is equal to the solubility of oxygen gas in Denver over the pressure in Denver. Now, we have 3 out of these 4 variables. We can start to replace things here. The solubility of oxygen gas in water at sea level is 1.25 times 10 to the minus 3. And the pressure at sea level is going to be 1 atmosphere. That's what's implied when we say sea level. Now we're trying to figure out the solubility of oxygen gas in Denver, but we do know the pressure in Denver at 0.8 atmosphere. So now that we've set this up, the rest of this is just a math problem. We want to solve for the solubility of oxygen gas in Denver. That's going to be equal to 1.25 times 10 to the minus 3 multiplied by 0.8 atmosphere, all divided by 1 atmosphere. Now we're essentially just dividing by 1, so we can go ahead and just ignore that portion anyways. Now, how are we going to solve this calculation right here? So what I'm going to do actually is I'm going to rewrite these values right here as fractions. So 1.25 can be written as 5 over 4, and 0.8 can actually be written as 8 over 10. And then that's all going to be multiplied by this times 10 to the minus 3. We're not going to ignore that. But what happens here is this becomes a lot easier of a calculation because we can do some simplifications. 4 and 8 are divisible, so 4 becomes 1, 8 becomes 2. And 5 and 10 are also divisible. We'll divide both by 5 and we get 1 over here and 2 over here. And essentially what we're left off with is 1 multiplied by 1, which is just 1, times 10 to the minus 3. So the solubility of oxygen and water in Denver is just 1 times 10 to the minus 3. And that is going to be answer choice A. Let's go ahead and tackle 10. Problem 10 says, given that the gases at the center of the sun have an average molar mass of 2 grams per mole, compressed to a density of 1.2 grams per cubic centimeter, under 1.3 times 10 to the 9 atmosphere of pressure, what is the temperature at the center of the sun? So in this problem, we're going to use the version of the ideal gas law that includes molar mass and density since we're given that information in the question stem. This equation is that molar mass is equal to density multiplied by temperature and the ideal gas constant all over pressure. Now our goal is to solve for temperature, so let's isolate this variable and redefine this equation as temperature is equal to molar mass multiplied by pressure over density multiplied by the ideal gas constant. Now the ideal gas constant, R, is equal to 0.0821 liters times atmosphere over moles times Kelvin. And this is important for us to write because we want to make sure that all our variables have the appropriate units before we plug them into this equation. Now we're given pressure in units of atmosphere. Perfect, we don't have to change anything here. We're given molar mass in units of grams per mole. Also good, we don't need to play with this at all. We're given density in units of grams per cubic centimeter. Now here, we want to modify this to grams per liter so that the units liter cancel out appropriately and grams also cancels out appropriately. So we have that density is 1.2 grams per cubic centimeter. Now 1 cubic centimeter is equal to 1 milliliter, so this is also equal to 1.2 grams per milliliter. And now we can convert this to liters by multiplying by the conversion factor. All right, 1 liter is equal to 1,000 milliliters, and this gives us our density as 1,200 grams per liter. Now we have all the variables and their appropriate units. We can go ahead and plug things into our equation. Molar mass is equal to 2 grams per mole. And pressure is equal to 1.3 times 10 to the 9 atmosphere. This is divided by our density, which is 1,200 grams per liter, multiplied by our ideal gas constant, 0.0821 liters times atmosphere, divided by moles times Kelvin. Now, before we do any of the calculations or approximations that we need to make to do the calculations, let me show you how all of the appropriate units cancel out and we're left with only Kelvin, which is perfect because we are calculating temperature. So here you see grams cancel out, moles cancel out, liters cancel out, atmospheres cancel out. We're left with units of Kelvin. Again, perfect because we are calculating temperature. Now, how are we going to approximate things? Well, we'll keep the numerator as is because it's really easy. 2 times 1.3 times 10 to the 9. That just gives us 2.6 times 10 to the 9th power. Now, what about our denominator? I'm going to round the ideal gas constant to just 0.1, and then I'm going to round 1,200 to just 1,000. So then we have 1,000 multiplied by 0.1. That is going to give us 1, 2, 3. That is going to give us a value of 100 in our denominator. So essentially what we have here is 2.6 times 10 to the 9 divided by 100. And that is going to give us 2.6 times 10 to the 7th power. You can think of this as 1 times 10 to the power 2, and 9 minus 2 is equal to 7, which is how we did that division. So looking at our answer choices, this best aligns with answer choice C. So 10 is C. Let's move on to problem 11. 11 says the gaseous state of matter is characterized by which of the following properties? Statement 1 says that gases are compressible. Statement 2 says gases assume the volume of their containers. And statement 3 says gas particles exist as diatomic molecules. Okay, let's go over statement 1. Gases are compressible. This is true. Gases are easily compressible because they travel freely with large amounts of space between molecules. So this statement is true. Statement 2 says gases assume the volume of their containers. Now, because gas particles are far apart from each other and in rapid motion, they tend to take up the volume of their container. So this statement is also true. Statement 3 says gas particles exist as diatomic molecules. Now, many gases do exist as diatomic molecules, but this is not a property that characterizes all gases. So this statement is not true. Only statements 1 and 2 are correct, which makes the correct answer for problem 11 answer choice B. Let's go ahead and tackle problem 12. Problem 12 says a gas at a temperature of 27 degrees Celsius has a volume of 60 milliliters. What temperature change is needed to increase this gas to a volume of 90 milliliters? Now, to solve this problem, we're going to need to use Charles' law, which states that the volume of a gas is directly proportional to its temperature in Kelvin at constant pressure and number of moles. So mathematically, Charles' law is expressed as V1 over T1 is equal to V2 over T2. Now we're given 3 out of these 4 variables. We know that V1 is equal to 60 milliliters, V2 is equal to 90 milliliters, and T1 is equal to 27 degrees Celsius. Now we're going to have to go ahead and convert that to Kelvin here so that we can use Charles' law. We can do that by adding 273. What we get then is going to be a temperature of 300 Kelvin. Now let's rearrange this equation to solve for T2. T2 is equal to T1 multiplied by V2 divided by V1. T1 is 300 Kelvin, V2 is 90 milliliters, and V1 is 60 milliliters. Notice that milliliters cancel out. Our final answer here is going to be in units of Kelvin, which is perfect since we're solving for T2. Now let's do this math. 300 times 90 is going to be 27,000, and that's going to be divided by 60. We can cancel out the 6's here, and now we just have 2,700 divided by 6. This is going to get us 450 Kelvin. So T2 is equal to 450 Kelvin. Now let's go ahead and convert this back into Celsius. 450 minus 273 gets us 177 degrees Celsius. Now the question asks us what temperature change is needed to increase this gas to a volume of 90 milliliters. We've gone from 27 degrees Celsius to 177. So 177 minus 27 is equal to 150 degrees Celsius. There was an increase of 150 degrees Celsius to go from 60 milliliters to 90 milliliters. And so the correct answer for 12 here is going to be answer choice B. All right, let's go ahead and move on to problem 13. 13 says, how does a significant decrease in temperature and volume affect ideal gas behavior, respectively? A says both lead to more ideal behavior. B says a lower temperature leads to deviations from ideal behavior, while lower volume causes more ideal behavior. C says a lower temperature leads to more ideal behavior, while lower volume causes more ideal behavior. All right. And then D says both lead to deviations in ideal behavior. Now, let's think about this. A decrease in temperature leads to a decrease in the kinetic energy of the particles, so intermolecular interactions become more significant. This change leads to deviations from ideal behavior. Okay, so that's for temperature. Similarly, decreases in volume, this causes the volume of the particles themselves to become more significant. This change also leads to deviations from ideal behavior. So both of these changes lead to deviations in ideal behavior. That makes the correct answer for 13 D. Awesome. Problem 14 is next. Problem 14 says, in which of the following situations is it impossible to predict how the pressure will change for a gas sample? Let's work through each answer choice. A says, the gas is cooled at a constant volume. Now, according to Gay-Lussac's law, if the gas is cooled, temperature decreases at a constant volume, the pressure is going to decrease. This relationship is predictable and direct, so this is not the correct answer choice. B says, the gas is heated at a constant volume. So if the gas is heated, temperature increases at a constant volume. What will happen to the pressure is that it's going to increase. This relationship is also predictable and direct, so it's not the correct answer. Answer choice C says the gas is heated and the volume is simultaneously increased. So in this scenario, both temperature and volume are changing. If the gas is heated, we're increasing temperature and the volume is increased simultaneously, then the effect on pressure really depends on the relative changes. If the temperature increases more significantly than volume, then the pressure may increase. If the volume increases more significantly than the temperature, then the pressure may decrease. Without specific details on the magnitude of these changes, it's impossible to predict the outcome for pressure, the exact outcome for pressure. And so the correct answer here for 14 is going to be C. Our last and final problem, let's tackle it. Experimenters noticed that molar concentration of dissolved oxygen in an enclosed water tank has decreased to 1/2 its original value. In an attempt to counter this decrease, they quadruple the partial pressure of oxygen in the container. What is the final concentration of the gas? All right, so let's tackle each of these changes individually. So we have original concentration of dissolved oxygen, and this concentration decreases to 1/2. So the current concentration is divided by 2. Keep that in mind. Now, what do? They also quadruple the partial pressure. So if the original partial pressure is P0 and the experimenters quadruple it, then the new pressure is going to be 4 times the original pressure. Okay, so we have these two things right here. Let's keep these in mind. What is the final concentration of the gas? Now, according to Henry's law, the new concentration is going to be calculated as Henry's constant multiplied by the new pressure. Now, we've defined the new pressure. Let's go ahead and plug this in. We have Henry's constant multiplied by 4 multiplied by the initial pressure. Now, Henry's constant multiplied by the initial pressure gives us our original concentration, which is CO divided by 2. So we can go ahead and replace these two terms as C0 over 2. So now we have our new concentration is defined as 4 times C0 divided by 2. And 2 and 4, all right, these are related. We can divide both of these numbers by 2 to get 1 over here and 2 over here. And what we get now for the new concentration is that it is twice the original concentration. That makes the correct answer choice C, double the original concentration. Awesome. And with that, we've answered all our practice problems for this chapter. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.